Well, happy first day of the week to you. Although it is a Tuesday, it's still the first day of the week. And we are wrapping up the idea of convergence with this lesson on 9-5. So we'll spend the week on this, finishing up some more convergence tests to add to our repertoire. So if you're making flashcards, you'll have 4 more actually today for different convergence tests. We're going to talk about the integral test for convergence, p-series, harmonic series, and alternating series. So those 4 tests, which are all kind of related to each other, to help us determine if a series is converging or diverging. So let's look at our first example. The series 1 over 3n plus 2 is a quantity from 1 to infinity. Does it converge or diverge? So if we apply the nth term test here, and we say, well, what's the limit as n approaches infinity of the term 1 over 3n plus 2, we are going to get the result of 0, which is inconclusive for the nth term test. It doesn't tell us if it diverges or converges. The geometric test is not applicable because this is not a geometric series. The ratio test, if we look at the terms here, so 1 over 3 quantity, n plus 1 plus 2, and then times the reciprocal term, 3n plus 2 over 1, which gives us in simplified form 3n plus 2 over 3n plus 5. Okay, that is an indeterminate form. So then we apply L'Hopital, and we'll get 3 over 3, or 1. And in the ratio test, when you get something equal to 1, that's also inconclusive in terms of does it converge or diverge. So we need some more tests to help us out with this. So the first test we're going to talk about today is something called the integral test. So the integral test has some restrictions. It can only be applied to something that has positive terms. So let's keep that in mind. Specifically, the terms have to be decreasing. So that means each term must be smaller than the term before. So if those things are true, then the series and the integral of the function have the same behavior. They either both converge or both diverge. So let's look at what the integral does, and then that will be able to tell us what the series will do. It won't be able to tell us what it converges to, just whether it converges or not to something unknown, but what its behavior is. So let's see if we can apply the integral test to this. So a couple things we have to check. Is it continuous? Okay, in the terms, yes, we're not skipping any terms. Are all the terms positive? And yes, all the terms will be positive from 1 to infinity. And are all of the terms decreasing as n moves from 1 to infinity? And again, as we move through, the denominator continues to grow, which means that each term is smaller than the term before. So because it has met all 3 requirements, then we can apply the integral test. So we want to look at what the integral of this expression does. So what would the integral from 1 to infinity do of the function 1 over 3x plus 2 dx? All right, so this is an improper integral. So we change our upper bound to b. And then the integral is going to be a natural log. So we'll have the limit as b approaches infinity of the natural log of the quantity 3x plus 2 divided by the chain rule of 3 plus the constant c from 1 to b. And so we'll substitute our bounds. So we'll have 1/3 of the natural log of 3b plus 2 minus 1/3 of the natural log of 5. And when we put infinity in for b, we'll have 1/3 of the natural log of infinity minus 1/3 of the natural log of 5, which is infinity. This is a divergent then integral. And a divergent integral implies a divergent series because of the integral test. So if the conditions of the hypothesis are met, then you can integrate the function, and then the behaviors will be the same. One implies the other. A convergent integral would imply a convergent series. So let's move on to the next example. Does the integral of 1 over n rad n converge as well? Well, we can do the integral test to this and determine, because it is continuous, positive, and decreasing. So this is a general form of the integral test. Everything will converge, every function where 1 over x to a power will converge if the power is greater than 1. So the convergence of the integral will imply the convergence of the series. And then if you have the power where the power turns out to be less than 1, then the divergence of that integral will imply the divergence of the series as well. So this is a special case. It's kind of a generalization. You can prove each of these with the integral test. The integral of 1 over x to the p will always converge. The integral of 1 over x to the p will always diverge if the power is less than 1. So let's sort of check that out. Well, we can say, yes, we can summarize this into the form n equals 1 to infinity of 1 over n to the 3/2. So since p in this case equals 3/2, which is greater than 1, okay, the integral will converge and the series will converge. So the integral and series both converge. So let's check that out here. All right, just making sure the hypothesis is met. It is continuous, check. It's positive, check. And it is in decreasing terms. Each term is smaller than the term before, check. Therefore, we can think about rewriting this integral, this series, n to the 1/2 over n to the 3rd becomes 1 over n to the 5/2. And p equals 5/2, which is greater than 1. So both the integral and series will converge by So we generalize that to a test called the p-series test. So anything written to the form of 1 over n to the p is called a p-series. The terms need to be continuous, positive, and decreasing. And so since one, then the other. So we call this the p-series test. So if it's greater than 1, the integral and the series will both converge. If it's less, the p is less than 1, then the integral and the series will both diverge. So that leads you hopefully to the next logical question, which is, what about p equals 1? What happens then? All right, so if we've established there's always these you know, not everything is covered. There's always these loopholes that we have to think about. So what about if the power is actually equal to 1? So when you have a power that is equal to 1 in a series form, it has a special name. It is called the harmonic series. So it is written this way: n equals 1 to infinity 1 over n. You need to be on the lookout for that. That is going to show up more often than not. This is the name of this series is the harmonic series. And so it will be, because this is so frequently going to pop up, we need to know, will a harmonic series, which is p being equal to 1, converge or diverge? So let's investigate that. Let's prove that. There are a couple ways that you can use to prove the convergence or divergence of the harmonic series. So let's look at what the harmonic series is so that you are able to recognize it. The harmonic series is 1 plus a half plus a third plus a fourth plus a fifth, etc. So that is called the harmonic series, so be on the lookout. All right, the question is the convergence or divergence of that. Well, I want to do a comparison here. So let's set this aside for a moment. Okay, and compare that side by side to another series. So what I'm going to do is, if the fraction is not a power of 2, I'm going to replace it. Okay, if the fraction is not a power of 2, I'm going to replace it. So I'm not going to replace 1. Why? Because that's a power of 2. That's 2 to the 0. I'm not going to replace a half because that's a power of 2. That's 2 to the negative first. 1/3 is not a power of 2. So I'm going to replace it with the closest power of 2, but yet smaller, not exceeding it. So I'm going to replace that with 1/4. I'm going to do that in a different color just to show that I've replaced it. So that used to be 1/3, but I'm going to replace it with 1/4. And then there's the actual 1/4 in the problem. Then comes 1/5. Well, that's clearly not a power of 2. So I'm going to erase that and replace it with the next power of 2 that's still smaller than that. That would be 1/8. So I'll put that here. And then 1/6 is not a power of 2, so I'm going to replace that with 1/8. Neither is 1/7. And then there's the original 1/8. And then I start replacing all the next terms with 1/16. There's a whole bunch of them up until we get to the actual 1/16. Okay, this is called a term-by-term comparison. Which of these two series is bigger? Just thinking term by term. Well, if we just do the first two, they are the same. But then the third term is comparing a third to a fourth. So the 1/3 is bigger than the 1/4. And then, so just by that fraction alone, we've got an inequality that's set up like this. So we have our harmonic series on the left is going to be larger than the series on the right. This is called a comparison. Okay, now let's look at the series on the right. I'm going to do a little grouping. All right, so what happens if I start to group things? So let me group all the 1/4 together. And let me group all the 1/8 together. And then I'll group all the 1/16 together. So I'll have 1 plus a half, and then the two 1/4 grouped together, they make a half. And you know what? The 4 1/8 together, they make a half. And there are going to be 8 1/16, and they're going to group together to make a half. And all of the powers of 2 that group, similar powers of 2 that group together will all make a half. What does this sum do? This is 1 plus a half 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 plus a half. This grows to infinity. It has a sum, so it is divergent. Well, let's think about our original series. It's on the other side. The harmonic series is bigger than that. So if the harmonic series is bigger than something, a series that diverges, then the harmonic series, by comparison, must diverge also. So that statement right there, you're not going to have to prove that over and over again. But knowing to recognize a harmonic series either in its summation form, okay, so either it's going to show up, pop up like this, and you do, oh, that's harmonic, or it might show up in its infinite form, or dot, 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 it keeps going, oh, that's harmonic. Either way, you need to recognize that there's harmonic and it is divergent. Okay, that's going to be important because it's going to show up so much. Okay, know that that is divergent. We've proved it by comparison. You could also prove it by doing the integral test. The integral diverges, therefore the harmonic series will diverge as well. Now there's a special case of the harmonic series called the alternating harmonic series, and that's where the harmonic series is preceded by a -1 to the n plus 1 power. So what does that look like? So if we start with plugging in the number 1, we get the term 1. If we plug in 2, we get -1/2. If we plug in 3, we get +1/3, and then -1/4, and then +1/5, and then -1/6, etc. So this is a special case of the harmonic series called the alternating harmonic series, and it is recognizable most quickly by -1 to the power in here, but you can also recognize it in its infinite form. So will this converge or diverge? We know the harmonic itself diverges. What will the alternating harmonic do? Okay, that's the big question. So then we need another test, because the tests we've had before, I'm going back, only apply to terms that are all positive. So this is a continuous, decreasing, but not positive, so none of the tests we had before work. So we need another test, and so this is called the alternating series test. So this is what you do if you don't have positive terms, but they have to be alternating. They can't be all negative. Okay, they have to be alternating. So you will have convergence if the following conditions are satisfied. Condition number 1, each u term is positive. You might be going, wait a minute, you just told me we were dealing with all negatives. Okay, the negatives are the signs. So there's a negative followed by a positive followed by a negative. But if the u's themselves are all positive, it's like absolutely positive. Okay, so that has to be true. It's a fancy way of saying it. Your alternating has to happen with a positive followed by a negative, positive followed by a negative. Okay, the second is that it has to be decreasing. Okay, each term must be smaller than the term before it. Okay, so u sub n plus 1 must be smaller than the term before it. Now the additional thing is it can't just be decreasing in general. The third requirement is that it has to be decreasing towards 0. The last term needs to be approaching 0. Now all the other ones before this, they could just be decreasing randomly to any number. It could be decreasing to 7 or decreasing to 14. This has to specifically be decreasing to 0. So if those conditions are met and it's an alternating series, then it will converge. So this is something that we say is conditionally convergent. not absolutely, but conditionally convergent, because it had to meet such stringent conditions in order for the alternating series test to apply. So let's go back to the alternating harmonic series. All right, so here are the conditions. Is it alternating? Okay, that's this part of it. That -1 to the power. Yes. Okay. Is it otherwise positive? So other than the alternating, so that's this part of it. Yes. Is each term, the 1 over n part, okay, is that decreasing? Yes, each term gets smaller. And finally, is it approaching 0? And 1 over n, as n approaches infinity, does approach 0. So we say, since the conditions are met, the alternating harmonic series is conditionally convergent. The regular harmonic series is divergent. The alternating harmonic series is conditionally convergent, and any other alternating series that meets the same specifications, that meets the same conditions. All right, so I'm going to try and summarize what we have been working on the last several weeks. How do you work your way through this sort of flow chart? Always start with the nth term test. Is the limit of the nth term 0? If the answer is no, then the series diverges. Anything non-zero. If it's yes, it's inconclusive and you need to move on to the next test. So then we move on to the geometric. Is this a geometric series? If the answer is yes, then you have converges if the absolute value of r is less than 1, diverges if not. Okay, or inconclusive if it's equal to 1. So if it's not geometric, we move on. Okay, can it be a p-series? Okay, well then if it is that, then it is convergent if p is greater than 1, divergent if p is less than 1. If it's equal to 1, inconclusive. If it's not a p-series test, then we move on to, does it converge absolutely? Can I use my absolute value? All right, so then we can check lots of these. We can check the integral test. We could check a comparison test. We can check the ratio test. All right, all of those have their own requirements. If those are inconclusive, or if the requirements of those are not met, all right, so for a ratio test, you have to have the limit of the two terms, and then you come out with your L, which is going to be, less than or equal to 0. If you have an integral test, your terms have to be positive and decreasing. If that isn't met, you can try a comparison test if you can't. Okay, so you just keep working through. The last choice is it an alternating series? So then if it is an alternating series, then you're going to check the conditions to determine if it's yes or no. If it's not an alternating series, okay, then we're going to add a few more tests later this week to finish it up. So hopefully that kind of puts you into sort of a hierarchy of the things you can try, working your way through, is it this, yes or no, check, move on to the next step if you're not done. So I know it's a lot, and it just comes with practice and being able to identify. If you can spot a geometric series right away, that's great. If you can spot a harmonic series or an alternating series right away, great. Some of those things are quick. P-series are super quick to spot if you can spot a P-series test. Okay, so hopefully you can kind of be honing your skills to be looking for some of the obvious ones. And for some of the less obvious ones, then you'll use things like the ratio test or the integral test. Okay, all right, we'll work on this together tomorrow in class. So tonight you'll work on this on your own, and then we'll straighten out anything that I didn't teach well or that you're confused on. All right, see you then. Bye.